Okay, so what I mentioned last time is that we're going to be, well, first of all, we're going to start with a prayer. Father, Son, Holy Spirit, amen. Bless us, O Lord, and these I get. Oh, what? I'm not eating. I'm kind of hungry, though. I haven't had lunch yet. Hail Mary, full of grace, the Lord is with thee. Blessed art thou among women, and blessed is the fruit in thy womb, Jesus. Holy Mary, Mother of God, pray for us sinners, now and at the hour of our death. Amen. Mary, Queen of Victory! You must all be muted. Okay. So if you do have a question, it's okay for you to chime in. I'm not really, I suppose I could have the chat function there. Close that out. All right. And then if there's something that I'm talking about and you can't see that, just let me know. But I'm not going to go on the book. I got to start the recording. I don't think I started it. Yes, I did. I started recording it. Perfect. Okay. So we're going to talk about limits. And if you remember, limit of a function is the height it approaches as x approaches a certain value. So that's the of a function. Remember, we're talking about functions, so things that only have one height output for the input. All right, so I'm going to go to the whiteboard. If you can't see a whiteboard, you're gonna have to let me know. But anyway, so let me go in, and then everybody can see that, hopefully. I'm writing the limit of a function f of x is the height that f approaches as x approaches a specific value. Now, when we have that specific value, that means from both sides. Okay, so if you don't designate a side, like only saying from the right or only saying from the left, which we will do that in section 1.6 and 1.7, then you have to assume that we're approaching from both sides. Okay, so that's what the limit of a function is. It's shorthanded by this. It's the limit as x approaches a of f of x. So the limit as x approaches a of f of x exists and equals L. They use capital L for limit. Is how we can shorthand this. And then I'm going to give you the formal definition from section 1.5. So really today and tomorrow for sure, I'm doing 1.4 and 1.5 together. 1.4 uses a specific window around x equals a, and a specific window around the height L that that function approaches. And then in section 1.5, it does it in general. So sometimes it's easier to do things in general and then go back and look at the specifics. Okay, so I'm going to go ahead and erase this, and let's look at a specific example, shall we? So an example, so we're going to look at this in concept first from section 1.4. So this is, we're going to let f of x equal x plus 1. Very simple function. We know what the graph looks like, right? I'm going to graph it over here. So x plus 1 has a slope of 1. It has a y-intercept 0, 1, right? Slope of 1 looks just like this. And what we're going to do is we're going to look at the limit as x approaches 1 from both sides of f of x, which is actually, f of x is actually x plus 1, so I can put that in there. And then the question is, what height, as x approaches 1 from both sides, what height do we approach on the graph? And the answer is obvious in this case, that we're going to approach a height of 2. So the limit as x approaches 1 of the function x plus 1 exists and equals 2. We're going to actually end up proving this as well. But what I want to do is I want to kind of show, hopefully using different colors. Need something that looks a little different here. But as x approaches 1 from the right, let's kind of look at this. We have x and then f of x. Let me approach 1 from the right. What do I mean by that? Well, if x equals 1.1, I'm just a little bit to the right of x equals 1, right? So if I plug in 1.1 into my function, x plus 1, I get a height of 2.1, right? So what I want to do is I want to get a closer and closer and closer to 1 without actually touching it. Perfect. So if I let x equal 1.01, then I'll 1.01 plus 1 in our function is 2.01. If I get 1.001, I'm going to approach, or this actually equals plugging in 2.001. And as you notice, as x approaches 1, I'm actually approaching a height of 2, and really it's coming in from above, right? So I'm approaching a height of 2 from above. So the way that we can draw this here is just put an arrow. So basically x approaches 1 from the right, so there's a little plus sign. And then f of x, my height, actually approaches 2. That's also from above, which means from the top. So that little plus sign in the exponent means from the right or from above, or from the right for x's, and from above or from the top for the y's, or f of x's. So anyway, we are approaching a height of 2 when we approach from the right. So now let's go ahead and look at approaching from the left. I want to approach 1 from x equals 1 from the left. And then if I do that, try and give myself a little more room, x and f of x, a number from the left would be like 9/10. So that's less than 1, but close to 1. If I plug that in to x plus 1 here, I'm going to get 1.9. So if I say, hey, I want to get closer and closer and closer to 1 from the left, then I could get closer by saying, hey, I could plug in 0.99 plus 1 is 1.99 for my height. And if I plug in 0.999, add that to 1, I'm going to get 1.999, and it's pretty obvious what's happening here. What we're actually doing is we're approaching the graph that filled in blue dot, but we're approaching a height of 2 from below. So as in this case, x is approaching 1, that's a 1, supposed to be a 1, hopefully it's on there, from below or from the left, then my height is actually approaching 2 from below or from the bottom, okay? So as following the red, as x gets closer and closer and closer to 1 from below, my height gets closer and closer and closer to 2 also from below or from underneath, okay? So anyway, so that's ultimately what we're doing. And so long story short, it's fairly evident that the limit as x approaches 1 of f of x equals x plus 1, it does exist and equals a height of 2. So remember, the limit of a function is the height that it approaches as x approaches 2. So I do have my side thing open. I'm not sure. I should get a notification or something if somebody does have a chat question. Or like I said, if you have a question as I go, I prefer that you actually just unmute yourself and talk to me. Everybody's, I assume, still hears me okay. And then what's nice about this board is I can actually erase it a lot easier than the board in a room, right? So, all right. So hopefully that makes sense. Now the question is, what do we want to do to prove this? What do we have to do to prove that the limit as x approaches 1 actually exists and equals 2? Before I do that, I want to look at another example that's very similar. So we're going to look at the limit as x approaches 1. Once again, if I'm not designating a side from the right or from the left here, then that means from both sides. But what I'm going to do for my function is my function now is going to be x squared minus 1 over x minus 1. And what we notice is, since this is my function f of x there, what happens is this is equivalent to, or actually equal to, x plus 1 times x minus 1 divided by x minus 1. So that should have actually been, it's equal to that. This function here is f of x equals this function here. And then what I can say, it's equal to that, but then if I cancel out these, then I have to say it's equivalent. So it's equivalent to x plus 1, but where is it equivalent to x plus 1 at? On the domain of f. So I'm going to call this, this is my function, this actually equals f of x here, right? So if I look at this and I were to graph this thing, the graph is going to look exactly the same as what I just had for a while. So it has a y-intercept of 1, but when I get over to x equals 1, I actually have a hole at a height of 2. And so the graph is exactly the same as what I just had, a line with slope of 1, except it has a hole at the point 1 comma 2. Okay, does that make sense? But now the question is, if I plug in, you know, before when I had f of x equals x plus 1 and I plugged in 1 into that, I get a height of 2. And so actually it exists there. But the domain of f in this case is all real numbers minus the set containing 1. Because if I plug in 1 to my actual function is in the box, it would be 0 divided by 0, right? Which is actually indeterminate. And so ultimately we need more information. Well, by the graph here, if I want to take the limit as x approaches 1 from both sides, we can do a similar concept. I was using, I should have been using red from the right, so I'm going to switch that now. I'm going to use red from the right, but I'm going to approach x equals 1 from the right. Well, as you can see, I should be approaching that open hole. And if I do that, let me just go from the right here, but x and then f of x, that's not very good, x, looks like a lambda. But anyway, if I plug in 1.0, or excuse me, 1.1, but I plug it into f is here. So really it's 1.1 squared, which is 11 squared is 121, right? So that's 1.21 minus 1 is 0.21 divided by 0.1, and that actually ends up equaling 2.1, right? Similarly, if I plug in 1.01 into the function, it's okay to do because I'm not excluding 1.01 from my domain, I'm only excluding 1. But if I square 1.01, I don't have my calculator on me, and then subtract 1 and then divide by x minus 1, then we're going to get something a little closer. X equals 2. So I'm just going to do that real quick, let you catch your thoughts, see if you have any questions. But 1.01 quantity squared minus 1 equals, it's 0.0201, and then divided by 0.01 is 2.01. And so I'm going to guess that maybe the next one, if I put in 1.001, could be 2.001. Long story short, this side approaches 1 from the right, and this side, the height actually approaches 2 from above. So, which is what we expect. But once again, I don't have to be defined there. So in this case, the limit as x approaches 1 from the right is actually equal to 2. I could do something very similar like I did from the left. So green from the left, I guess. So if I plug in, once again, if I plug in x equals 0.9, that's okay too. And then f of x, so it's 0.9 squared, which is 0.81 minus 1, which is minus 0.19, divided by that is, anyway, it should end up being 1.9. I'm going to guess that if I plug in 0.99, I'll just do this one quick, square that one out. It's 98.01 or I don't know, minus 1 equals 9,800 divided by 0.01 is, well, I'm doing something wrong there. So 0.99 squared, 0.9801, there we go, minus 1 is minus 0.0199 divided by 0.01 is, well, I don't know, but it's 1.99. Anyway, I'll let you continue this, but once again, I'm approaching 1 from the left in this case. My height is actually approaching, running out of room here, this approaches 2 from underneath, from below. So once again, I'm coming in here. So the same exact thing that I had before, but the limit as x approaches 1 of this thing actually does exist and equals 2. So 2 is my limit L. So L is 2. That's the height I approach. So the question is then now, how are we doing this and formally to prove that it's a limit when we don't necessarily know what the graph looks like or those types of things, or have a more awkward function. So there's actual proof of this as well. So I'm going to jump in to section 1.5, and then we'll circle back at 1.4 with a specific thing here. So let me erase that. I'll see that anybody has any questions. Okay, so let's look at the formal definition. This is the formal definition of limit. So this is something that you need to know. This is also something that you're going to have to use and prove. First, let f, if I use an f, it's a function. So the book would say let f be a function, but we know it is, so I'm not going to write that. Let f be defined on some open interval containing x equals a. So in other words, I'm defined around x equals a. So in the previous examples, a was 1, x equals 1. Anyway, some open interval containing a. However, I do not have to be defined at a itself. So the second example we had a hole when x equaled 1. So containing x equals a, except possibly a itself. So I don't have to be defined there to take a limit. Okay, so we have this. So we got a lot of verbiage. Basically, the domain of f, what does this say? In general, this says the domain of f is either some open interval containing a, so x1 to x2, it's defined there, where a is an element of x1 to x2, or is going to be defined on x1 to a, not including a. Oh, that's terrible. It's going to be defined on x1 to a, not including a, union, not including a, to some point to the right, x2. So anyway, basically, if it was all numbers, it could be something like, hey, this is all real numbers, that's fine. All real numbers except the set containing a is fine too, to look at a limit. Okay. All right. So anyway, so keep that first part of the definition. Let f be defined on some open interval containing a except possibly a itself. I'm going to continue the definition of limit. then I gotta get where I can write. Then the limit of f of x as x approaches a remember that's from both sides if I don't restrict it to one side, going to exist and equals L, which is my limit, the height I approach, if and only if, so remember two F's, IFF is if and only if, so definitions go both ways. If and only if there exists, excuse me, if and only if, sorry, for all epsilon greater than 0, this is where for all epsilons greater than 0, there exists a delta greater than 0 such that zero is less than the absolute value of x minus a is less than delta. Sorry, delta is given by, I got to change colors here. Delta is a it's like a funky looking D. So there's a delta greater than 0. Epsilon, let me use a different color. Epsilon is going to be like a looking E, capital E, greater than 0. So anyway, so we're gonna, delta is like a squiggly little D. It's almost like a capital F, right? But it's really a small D. Epsilon is kind of like a E, like that, almost like an Asian notation, except it's rounded. All right, anyway, let's get back to the definition. The limit of f of x as x approaches a exists and equals L if and only if for all epsilons greater than 0, there exists a delta greater than 0 such that 0 is less than the absolute value of x minus a is less than delta, implies or guarantees that the absolute value of f of x minus L would be less than the epsilon that was given. Okay? And then, so we have that. This is from section 1.5. So if you're starting to hit panic mode because you're like, oh my gosh, I didn't know calculus was like this, look on page 41 in your book, and it's the blue box. Okay? And then I'm going to go back and I'm going to show you what that picture looks like. But this is page 41, blue box in your book. And then I'm going to go, and this is how it's written. It's written, the limit as x approaches a of f of x exists and equals L. Okay, that's how it's written. So this is kind of the shorthand. Once again, do you remember me saying that mathematicians like shorthand? Yes. And so I need to draw you a picture now of what this is really doing. Okay. So let's just look at a graph that had a hole in it. I'm going to bring the hole out here. So there's our hole. This is my height L. This is A. Now in this case, it's a line, f of x. This is f of x, right? So we had a line with a hole in it right here. So once again, we don't have to be defined at x equals a. We just need to be defined on some open interval around it. So as long as I'm defined around a, then I can talk about the limit of the function. Okay, once again, this is L. I know the height was 2 before. I know that A equaled 1 before, and L, my limit was 2 on both the examples that I gave you. But what I want to show you is really what we mean here. Okay, so what is epsilon? So let me go back to the definition. Let f be defined on some open interval containing a except possibly a itself. Then the limit exists and equals L if and only if for any epsilon greater than 0. So what's epsilon? Epsilon is a tiny number. It gives you a vertical window around L. So this is really L plus epsilon, and this is L minus epsilon, where epsilon is any tiny number. You can choose that tiny number. Anybody could choose it, and for whatever epsilon is given, that's going to create a corridor or a reverse mapping window that I need to make sure I stay inside of. So L could be, I like to think of, hey, we had, I'm going to use a different color here, but we had 2 here. Well, we could go, you know, a tiny window could be 0.1 for epsilon, a tiny number. So we go from 1.9 to 2.1 for my epsilon window, and that's my limit L minus epsilon. So if epsilon would equal 0.1, then the epsilon window around my limit that I expect this to be would be 1.9.1. So hopefully that makes sense. Okay. And I gotta make sure I get my I'm going to give myself a 2-minute warning here too. On here. All right. So anyway, if I reverse map it, basically what I have to do is I have to find a delta small enough so that A minus delta to A plus delta, if I have a delta window for any epsilon that you give me, I need to be able to find a delta window around x equals A such that every single mapping from these x values to their heights actually all would end up mapping inside of the epsilon window. So if you give me an epsilon, I can find a delta. So you give me an epsilon, if I can find a delta greater than 0 such that any x values, so we'll call them, you know, x sub I, so x sub 1, x sub 2, x sub 3, whatever, any of these x values would get mapped inside that delta. When that's actually the case, and I can prove that that's the case, then the limit exists and equals L. So the best way to learn this is by seeing. And so when we have a proof, here's what we're going to do with the proof. So proving a limit exists by the formal definition, we're going to do a little thing called let and set. Okay, so if you let epsilon be some tiny number greater than 0, we need to do some work to find delta, and then we're going to set that delta, which is also greater than 0, because it's got to create a window. Remember, we got the blue window around L and we got the green window around A. We have to have a window. So even though epsilon is designed to be a tiny number, it creates a small vertical window around L. Delta could be a very tiny number as well, but there's some bigger deltas that could work. Our goal is going to be to find the smallest delta window that would, the biggest delta window that still makes this work. So we want to find the biggest window, so I could actually go out almost to the blue, right? I could almost go to those blue vertical lines and find that delta and actually get some additional values of x's that map in there. So I'll show you how to do all this. Chances are I'm not going to have it done efficiently until we're done with class tomorrow. So do not hit the panic mode. I'm not there. Do not, you know, don't worry. Pray, hope, don't worry, right? St. Padre Pio. So we're through this together, just like High School Musical 1, 2, 3. You know what I'm impressed is, like, everybody's still there, apparently. I'm going to look. I'm going to go back to the class. I just want you to wave at me. I got to figure out how to do that. Let's see. I don't know how to do that. Oh, there. Yeah, I see Jordan. Like, Jordan's the only one. Are you the only one there? I know you're not, but I don't know if I know how to. Trying to figure out how to see everybody. Somebody needs to talk. I don't know. Show me, turn
I'm here. We're all here.
Well, I know you're there. But where are you going to go? Are you going to go roam the hallways and then get tackled by a police officer and then handcuffed and taken off because you're trying to skip calculus? No. All right. Anybody got any questions? Good time for a break. Any questions? No? All right. Anyway, you'll all get this, but I'm going to guess that you don't really get it yet. Okay. And so this is why when I said go back and read 1.4 and 1.5, try to work through the exercises, try to follow their examples. That's what we're going to do. So I'm going to start with that formal definition, but I'm going to start with 1.4 example. Like I'll go back to the example and say, okay, how do we do that then? And then I got to share my whiteboard. There. All right. Are you ready? So let's look at the first example where we had the limit as x approaches 1 from both sides of x plus 1. Let's start with the one that didn't have the whole exists and equals 2. So what I'm going to do is I want to say let epsilon equal 0.1. So 0.1. Then what we need to do is find the delta greater than 0 such that what happens? 0 is less than the absolute value of x minus a. So what's a? A is right here. So this is, I'm going to go back. This is a, at 1. And then 2 is L, right? And then right here, this is f of x. Okay. So now this is only for one particular value of epsilon, but on the formal definition, we have to do it for any such epsilon, but I'm going to show you how to do it in general. The absolute value of x minus a would be the absolute value of x minus 1 would have to be less than delta, and that would imply or guarantee that the absolute value of f of x, which is x plus 1, minus L, which would be, we think it's 2, would be less than epsilon. So hopefully you can see that. Anyway, so then what is that? We're just going to keep working with the right side. So this right side says then if I simplify this together, this says that x minus 1 is an epsilon, but what's epsilon? That was given. So this equals 0.1, right? 0.1. So I could have just wrote, instead of epsilon, I could have put 0.1 in because that was given. So the absolute value of x minus 1 has to be less than 0.1. So I need to find this delta such that 0 is less than the absolute value of x minus less than delta, would imply the absolute value of x minus 1 is less than 0.1. So what do you think we should set delta equal to? We're going to set delta equal to 0.1 because that's going to work. So if I do that, I could simply just look at the right half of the equation and verify that that's the case. Once again, back on the graph, if I had this graph that we had before, and there's 2 and there's 1, my epsilon window would be 0.1. We did that in blue. So this would be 2.1, 1.9 to 2.1, and the reverse mapping back, the biggest reverse mapping back would be 0.1 above, so 1.1 and 0.9. So 0.9 to 1.1, basically every single x value in here would map inside that epsilon window that was given. Sorry, that's blue. Epsilon's blue. This is the epsilon window here around the expected limit. This is only for one. Of course, we'd have to do it for infinitely many, so I'm going to show you in section 1.5 how to do that efficiently. So let's go back and do the proof then. So I got to erase, start over. So proof. Let epsilon equal, all right, I got 2 minutes. I'm going to finish this one up. 0.1 set. So now we do the let set. So this is where the let set comes in. Set delta equal, we did our scratch work. So delta in this case is going to be the same, 0.1. Then 0 is less than the absolute value of x minus a. A was 1, is less than delta. We said is going to be 0.1. Implies, I can just look at the right side. I don't really need the left side here. So that implies that the absolute value of x minus 1 is less than 0.1. This is epsilon, so we're good. So basically, this is kind of section 1.4 stuff, but a really easy example of it. I'm going to have to show you how to do one that, you know, where it's not exactly the same. Sometimes you got to divide it by 4 or whatever. So if epsilon's 0.1, delta might be 0.1 divided by 4, 0.025. All right. So anyway, that's an introduction. Once again, it's a confusing introduction until we get going. And then tomorrow, I can do it in general. Let me get back to where I can see you. Can you guys see me? Probably not. Okay, so can't see me, or you can see me?
We can.
You can see me?
Yep.
Okay, awesome. All right, so biggest thing, don't panic, and realize that, you know, we're going to get through it together, more stuff tomorrow, but do minimally read 1.4, read 1.5, and go from there. I'm going to show you where I'm at, show you what's in my background. Has the bell rung yet, Luke? I can see Luke. Has the bell rung yet? You guys see anything behind me?
Yep.
Yeah, that's my parents' place. I did get to see my parents for the first time in over a year. So when you see your parents tonight, give them a big hug and say, you know, it would be hard to not see you for a year. So that was pretty cool for me to see them. I did do a blood COVID test before I came up, thanks to Carter's dad, and it was negative, so that part's good. So hopefully everybody's healthy. I got to let you go. I think the bell's already rung, right? Has the bell rung yet? Close.
10
All right, we're
seconds.
good. If you got questions, use WhatsApp so I can communicate with you that way. See you tomorrow. Same way, same bat station, same bat channel. Done. Nice.